Okay, let's move on to our last section of this chapter, which is on pH. So pH stands for the potential of hydrogen, and pH is actually a measure of the density of hydrogen ion in a substance, right? So if something has a lot of hydrogen ion in it, it tends to have a lower pH actually, and is considered acidic. And that's because hydrogen ions actually have a positive charge. So let's kind of just look at water and kind of see what we mean by it, because pH is actually a scale that measures the substance concentration of how many lone protons they have, but we tend to think of protons and hydrogen plus ion as pretty interchangeable. So when we have water, we actually have water that can dissociate into hydrogen ion and hydroxyl ions. Okay, so water can actually dissociate into hydrogen ion and hydroxyl ion. And when we have equal amount of hydrogen and hydroxyl ion, we actually have a pH of 7. So it's pretty neutral there. So if we're measuring the concentration, the substance concentration of how many lone protons we have, and as I mentioned, a lot of times we think of H plus, this guy right here, as equivalent to a lone proton. So one lone proton is equivalent to one H plus, hydrogen plus, right? So when we think of pH, we're thinking of how much hydrogen ions do we actually have in a solution. And this scale is measured on a scale of 0 to 14. So if we have equal amount of pH between, let me turn on this pen, I like it more. If we have equal amount of hydrogen and hydroxyl ion, we're right here. We're at pH 7, which is pretty neutral, right? As we add more hydrogen ions, we're increasing hydrogen, we're increasing our positive charge. We actually are moving down on the scale and things become more acidic. As we are losing, not really losing, but as we're adding other ions, that makes it so that concentration-wise of the total number of ions in a substance, that there are less hydrogen ions. So we're having less hydrogen ion. We're actually moving, right, decreasing the hydrogen ion right here, and we're increasing the hydroxyl ion. So that's another way to think about it, is we're actually increasing hydroxyl ion. Then we're actually becoming more basic or more alkaline. So this is neutral. This way movement is acidic, and this way movement is basic. And notice that this is tension negative 10, tension negative 3, tension negative 6, and so on, right? So you can see here that the pH is on a logarithmic scale, meaning that the difference between pH 0 and pH 1 is tenfold, right? So there are tenfold more hydrogen ions in 0 versus a pH of 1. So how do we change the scale, and what do we mean by this whole hydrogen versus hydroxyl ion? So if we have this, for example, in this situation, if we have something that is like, let's say pH 9, and we want to actually, or let's start the other way because we're going to do hydroxyl first. Let's say we have something that's pH 6, and we want to make it more neutral. We want to bring it back to pH 7. pH 6 means it has more hydrogen ions, and so in order to balance that out, right, and we want to have equal amount of hydrogen and hydroxide, we can actually add sodium hydroxide, because sodium hydroxide will dissociate in here and have Na and OH ion. And this OH, this hydroxyl ion right here, as we add more of it, we will actually bring out the concentration of the hydrogen ion in a pH 6, let's say pH 6, right? And we add more of sodium hydroxide. So we're going to say that we add more concentration of OH minus right? So by doing that, we actually will end up with a solution because we have decreased the amount of hydrogen ion. We can actually move it so that it moves toward a more alkaline or more basic. So let's say we want to move it toward pH 7, right? We would add more of the sodium hydroxyl because what we really want is this hydroxyl part. Okay, vice versa. Let's erase everything and start over. Oops. If we had a pH, let's say of 8, and we want to move it toward a pH 7. So let's say we start off with a pH of 8. Right? What do you think we need to do? If we have a pH 8, this means that we have less hydrogen ions. So what we want to do is we actually want this guy right here, this hydrogen ion. So we actually want more hydrogen ions. So by combining hydrogen hydrochloric acid, we can get more concentration of hydrogen. And by having higher concentration of hydrogen ion, we can then move it toward a pH of 7. And remember that this is logarithmic, so we're going to have to add a 10-fold different concentration between, sorry, got that message up there, between these two pH in order to actually see that. Okay, so the pH scale, as we mentioned, is a logarithmic scale. So each time that we move up, we're adding 10 times full of hydrogen ions in order to move from one pH to the next pH, right? So if we're looking at, let's say the difference between lemon, which is like usually like about pH of 2 here. So it says 10 to negative 2 because it's in logarithmic scale, but I'm going to write pH 2. Right? We want to see if we want to compare that to, let's say, coffee, which coffee, according to this, is about pH of 5. So how much more acidic is lemon compared to coffee? Oops, this was pH 5. I was about to write 3. Okay, so 5. So pH of 2 to 3 is 1. pH of 3 to 4 is 2. From 4 to 5 is 3, right? So that means that the pH difference between coffee and water is 10 to the 3, which means that it is 1,000 times. 1,000 times more acidic lemon is compared to coffee. So how about this question? How many more times acidic is a pH of 5 than a pH of 7? Well, from 5 to 7 is 10. There's a difference of 2, right? So that's 10. So that's going to make it 100 times more acidic. Oops, I just realized my head is right here, right? So it's 100 times more acidic to go from a pH of 5 than 7. Okay. And so why do we care? What do we do with pH? Like why do we, well, pH, we use pH a lot because it's really important for when we actually need to change the pH of certain substance. So let's back up and kind of look first at what salts are. So salts are compounds that can release ion other than hydrogen and hydroxide. So we already saw an example of salt in this chapter, right? We've been talking about sodium chloride. So when we dissolve those two, we have sodium ion and chlorine ion. And so those are both ions that can dissolve in water. So that's a salt. Buffer is different than salt in that they also have water, but they're typically used to keep a pH within its normal limit. So typically with a buffer, we use a buffer when we don't want the pH to change a lot. because we don't want the buffer, we don't want the pH to change a lot and it does this by taking up, the buffer will actually take up the excess hydrogen ion if we're adding too much like hydrochloric acid, for example. On the same note, it will take up the excess hydroxyl ion. So we typically want buffers in order to try to keep that pH consistent within something. So an example of this is in our blood. We want our blood to maintain a pH of 7.4. Like, we don't want to vary too much. Why do you think that is? Why is it that it's important that we have this buffer that allows our pH to stay within that 7.4 range? So we don't want it to vary too much. And it actually can make a big difference. If we vary too much, it could lead, in both ways, it could actually lead to death, right? Why is that? Well, it's because in our body system, in order for our body to function properly, we have a lot of molecules, which we will discuss later on, called proteins. And these proteins, they make these other substances called like enzymes. And so in order for our bodies to function properly, we need these proteins to function properly. So we need these proteins to be to have a very specific structure. And when the pH changes, it actually can change the integrity and the structure of these proteins and these enzymes. So when we change these the structure, it can actually lead to these proteins and enzymes and such no longer functioning. And if they don't function properly, then our body doesn't function properly. So we need to maintain a very narrow window of what we allow as far as our pH in our blood, because we need that pH to make sure that our proteins and our enzymes are functioning properly, because their structure isn't compromised. Okay, so this is an example of it, right? So if our pH gets too low, below 7.4, is also known as acidosis. And so you'll see symptoms of this. You'll see symptoms in that your heart rate will increase. You might get out of breath. You might feel kind of nauseous, like you want to vomit. You might get kind of headachy and kind of like confused. And so these are all examples of what can happen. And it's because, once we have our pH is too low, all of the different chemical reactions that is dependent on these different proteins in our body, they kind of get wrecked up, because the proteins, like I mentioned, are no longer able to function properly, right? So a lot of the chemical in the reaction in the body is pH dependent. On the same note, right, if a pH rises above 7.8, it can also lead to devastating conditions. So we want our pH within this very narrow range, and so that's why we have buffers in our blood systems to keep that pH within that certain range. So this is really interesting as well, especially for those of you that want to see how human impact influences our environment. I will link this in my list of links. But you can also watch it via this link right down here. I'll move my video over here. Okay, so this has to do with, again, human impact. We've been talking about how human impact can have a lot of different changes, and one of the things that human impact can have a change in is the acidification of ocean, right? So as we produce more carbon dioxide, this carbon dioxide gets absorbed by our water. It gets absorbed by water, and when it's the more carbon dioxide that gets absorbed by the water, the more the water and carbon dioxide can change and form these other compounds, these other molecules that can actually have devastating effect with regards to the pH of the ocean, which, again, similar to us, different organisms within the ocean have very sensitive like pH range in which they can survive in. So as we acidify the ocean, we actually are impacting our ocean a lot, because it affects all of these living organisms that actually live in the ocean. So we're not just talking about fishes and our coral, but just like the algae there, the plankton there, the plant life, the bacteria, all that gets really affected when we change the pH of the ocean. So watch the video. I find it interesting. And I will see you guys in the next chapter, chapter 3.